types of conductance. One is metallic and electronic. Okay, so both are that is same type. It may be called metallic conductance or electronic conductance. And the second type is electrolytic conductance. So first we will see what is metallic conductance. Electrical conductance. Electrical conductance, that is a common term. Okay, now electrical conductance, it may be through metals or some electrolytic solution. So when it is through metals, it will be called metallic or electronic conductance. Now why the name is electronic conductance? Because in the metals there is presence of electrons, and because of the movement of these electrons, basically we are getting this electrical conductance. So that is why metallic conductance, that is also called as electronic conductance. And this type of conductance, it depends on some factors: the nature and structure of the metal, fine, then the number of valence electrons per metal, that is per atom of the metal, and temperature. And the important thing is it decreases with increase of temperature. Okay, and another type is electrolytic conductance. So in this case, electricity, that is the electrical conductance, the reason behind it is ions, not electrons. In case of metal it is ions, but now it is, sorry, in case of metals it is electrons, but now it is ions, ions that are present in solution. Okay, so this type of conductance is called electrolytic conductance, or it can also be called as ionic conductance, because the species that is responsible for conductance is ions. So that is why the name is ionic conductance. So this electrolytic conductance, it depends on the nature of the electrolyte added. Okay, so what type of electrolyte is the electrolyte? Its dissociating power is very high or low, that is whether it is strong electrolyte or weak electrolyte. That is the nature of the electrolyte. Then size of ions produced, the ions that we are getting from the electrolytes, what is their size, whether it is small or large, and their solvation, that is how much solvated is the ion. So suppose we have two ion, one is X plus, another one is Y plus. In the solvent, suppose the solvent is water, so water molecules will surround this X plus ion and Y plus ion, but depending on the nature of these ions, it may be positive charge or negative charge, the solvation by the solvent molecules, that may be different. So depending on that, the conductance, that will also change. Fine. Now the nature of the solvent and its viscosity. Now the electrolyte that we are adding in the solvent, the nature of that solvent and its viscosity, that also matters. Concentration of the electrolyte, whether this is a concentrated solution of the electrolyte or concentrated or dilute solution of electrolyte, that is also important. And the last point, which is a major difference between these two types, in the case of electronic conductance, it decreases with increase of temperature, it is inverse relation. But now in case of ionic conductance, it increases with the increase of temperature. And what is the reason behind that, we also come to that point. But mainly in this chapter we will focus on ionic conductance, not metallic conductance. Okay, now what are the major difference between these two types of conduction? Metallic versus electrolytic conductance. In case of metallic conduction, obviously it is carried by the movement of electrons, but in case of electrolytic conductance, it is because of the movement of ions. That is the main difference. So that is why it is called electric conductance, and electrolytic conductance, that is also called as ionic conductance. No change in the chemical properties of the conductor. So the metals through which the electrons are moving, there is no change, that is no chemical change in the metal. So if it is a particular metal, it will remain that particular element only, it will not change to any other chemical species. Okay, but in case of electrolytic conduction, it can involve decomposition of the electrolyte as a result of the chemical reaction. So now in case of electrolyte, there may be decomposition. So suppose the electrolyte is AB and after decomposition it becomes A plus and B minus. So there is some chemical reaction going on, okay. It doesn't involve the transfer of any matter, but it may involve transfer of matter as ions, okay. So whenever there is ions, that is suppose from AB we are getting A plus or B plus, then in the form of ions matter may be transferred, but in case of metallic conduction that is not the case. Metallic conduction, and the last point which is very important, is decreases with increase in temperature, but here it is proportional with temperature. Now what is the reason behind it, why metallic conduction decreases with increase in temperature, that we have to know. So when we are talking about metallic conduction, that is in metals, conductivity, it is because of the free electrons. Free electrons, their movement is actually responsible for conductance. So when we are increasing the temperature, what happens? The positively charged kernels, suppose the metal atom is M, when electron is removed, now it is M plus. So this M plus is actually the positively charged kernels, okay. So that is also present in the sea of electron, and it can acquire mobility, and as these positive kernels it can acquire mobility, so it will obstruct the movement of these valence electrons, that is the free electrons movement. Now it will be disturbed by the movement of the positive kernels. And electrolyte, in case of electrolytic conductors, now here electricity is because of ions, not for electrons. So as ions are charge carriers, so with increase in temperature what happens? Ionization increases. So suppose the electrolyte is AB and it is ionized and as A plus and B minus. So when we are increasing the temperature, this dissociation will increase. That means number of ions will increase, and as number of ions are increasing, that means electricity will also increase. So that is why the relationship with temperature is proportional. But in case of metallic conduction, it is inverse, because here the movement of M plus also will increase with increase in temperature, and that will make some disturbance to the movement of the electron. So that is why the relationship of these two types of conductance with temperature is completely opposite, okay. Now as we have said, remember in this in the second box, that is the nature of the electrolyte added, on that the electrolytic conductance is dependent. Now nature of electrolyte means there may be two types of electrolyte, strong electrolyte and weak electrolyte. Here we have some examples of both of these types. So strong electrolytes are basically strong acids or bases and salts that are mostly fully dissociated. For example, NaCl, KBr, magnesium chloride. So here you can see that in the solvent is water, H plus and Cl minus ions. So you will not see any HCl, that is distinct HCl molecule. All the HCl molecules are dissociated to cation and anion. So dissociation is 100%. And in case of NaOH also, here this is Na plus and this is HO minus. So all there is no discrete NaOH molecule, all are present in dissociated condition. So if there are total 5 NaOH molecule, in the medium there will be 5 HO minus and 5 Na plus. But if it is weak electrolyte, now the dissociation is not complete, okay. So suppose if there are 10 molecules of weak electrolyte, only 2 of them will be dissociated or 5 of them will be dissociated, like that. And under weak electrolyte we mostly have weak acids and weak bases, fine. So in this picture it is very clear that how in case of weak electrolyte the dissociation is not complete. So here we have total 5 molecules. Suppose there is any compound, 5 molecules. Now out of these 5 molecules, only one molecule is dissociated to cation and anion. That means 1/5 is dissociated, so the degree of dissociation alpha will be 20%. 1 by 5, out of 5 only 1 is dissociated, so this is 1 by 5 multiplied by 100, so this is 20%. Similarly, out of 5 molecules, here 2 in undissociated form but 3 of them dissociated, so that means now out of 5 3 are dissociated. Okay, so that means it is 3 by 5, so it will be 60%. Now in the third case, only 2 molecules dissociated, so 2 out of 5 dissociated, so it will be 40%. 2 into 20. And in the last case, out of 5, 4 molecules dissociated, only 1 is undissociated. That means now the degree of dissociation 4 by 5 into 100, this is 20, so it is 80. Okay, so this is the case for weak electrolyte, depending on different types of electrolyte and also depending on the dilution, because when the solution is very dilute, then dissociation is increased. That means degree of dissociation will increase. And if it is very concentrated solution of weak electrolyte, degree of dissociation will be low. Fine. So here we have 3 examples. Strong electrolyte, so it is very bright, the light is very bright. For weak electrolyte, the light is there but it is dim, and for non-electrolyte, obviously there will be no light. Non-electrolyte means where you cannot expect any dissociation. All the molecules will remain undissociated. It will remain a single molecule. You will not find any presence of ions. And if there is no ions, obviously we cannot call it electrolyte. So it will be non-electrolyte. No ions means no electricity, and no electricity means no light. Now we have to know some terms. We have already seen what is conductance. It is the capacity of the flow of electricity. Now resistance, it is opposite of conductance. So if conductance is the capacity for the flow of current, obviously now it is a measure of opposition to current flow in an electrical circuit. And we have seen in case of conductance, the unit is ohm inverse. So here the unit will be ohm, because these two are related to each other inversely. So resistance, its unit is ohm, which is symbolized by this sign. And for conductance, which is opposite of resistance, the unit is ohm inverse. Now electrical resistance of any object, it is directly proportional to its length, that is L, and inversely proportional to its area of cross section. So suppose if there is any object which is having length L and area A, so this resistance R, it will be directly proportional to L and it will be inversely proportional to 1 by A. So adding these two, what we can write? We can write that R is proportional to L by A, and this L by A is known as cell constant, that is length per area. So for length, suppose the unit, if it is centimeter, so obviously for area it is centimeter square. So ultimately the unit of cell constant will be centimeter by centimeter square or meter by meter square. So ultimately it is meter inverse 1 or centimeter inverse 1. This will be the unit, that is inverse of length unit. That will be the unit of cell constant. And R is having unit ohm. So unit of conductance, it is ohm inverse. We can write it in this way. Now there are some other terms also used, and remember all these terms, because when you will see the numericals, different types of units may be mentioned. So ohm inverse and mho, these two are same. You can write it ohm inverse or mho, both are fine. And there is another unit which is Siemens. In short, it is written S. So basically all these are same. 1 Siemens is equal to 1 ohm inverse or equal to this sign we can use Greek letter omega or 1 mho. So all are basically same. Okay. So from this picture we can understand what is the relationship between current I, voltage V and resistance R. So resistance is expressed in ohm, volt we already know that it is expressed in V, and current, this is a new term we are seeing here where the unit is ampere, in short A. Now resistance I, current and volt V, these three are related to each other by this equation, and you can also write it as R V by I, or you can write it as V equal to IR. Okay, and this picture clearly demonstrate what is the relationship between these three. So volt is basically responsible for the flow of current. So higher is the amount of voltage, higher the current flow, this intensity will increase. But if there is high resistance, then current flow will be disturbed. Okay, now there is another picture where you can find some analogy, and that is analogy of water tank and pipe. So here in this water tank we have water, and this is the height of water starting from this point. So this height you can consider as voltage. So higher is this height, higher will be this movement of water, which is compared with current flow. So higher is the voltage, higher is the current flow. So V and I, these two are directly proportional to each other. And what is resistance here? So suppose we have a tap here, so we can control the flow of water. So if the tap is fully open, the water, that means there is no resistance. But if the tap is completely closed, that means resistance is in maximum power. So this is actually resistance, this is voltage, and this current. Okay, so in this way, if you can remember this picture, you can easily understand what is the relationship between these three terms. So V is directly proportional to I, but voltage, that is also, that is resistance and I, these two are inversely related. So when there is high resistance, then current, that will be very low, and obviously if resistance is high, how the current can be very high. So try to remember this analogy of water tank. It will help you to remember this equation, that is V equal to IR. So one term we have seen, resistance. Now two more terms, one is resistivity, another one is conductivity. Now resistivity, it is also known as specific resistance. Why you should remember all the names? Because in some cases there is, you will see specific resistance, this term is used. In some cases you can see that resistivity is used, though by IUPAC this term is should be used, but you can see the use of both these terms. So it is better you try to remember this. So specific resistance or resistivity. Don't think resistance and resistivity are same. There is difference. So we will see what is resistivity and how it is related to resistance. So in this object, this is the L, which is length, and this is the area, which is A. Now resistivity, it is denoted as rho. Okay, it is like P, but it is not P, it is rho. And resistance, which is mostly demonstrated by this sign. This type of sign means there is resistance. So resistance, we have already seen in the previous slide that it is directly proportional to L and inversely proportional to area. Now if you are removing this proportionality sign, you have to place a constant. So this rho is that constant, and it is known as resistivity. Okay, so this relationship you have to remember, because in numerical, if any of one of the value is unknown and other values are given, you can easily find out the unknown variable. Okay, next is conductivity. Now, as you have seen here, resistivity can also be called as specific resistance. So conductivity can also be called as specific conductance or sometimes specific conductivity. So what is conductivity? It is nothing but the reciprocal of this rho. So it is simply 1 by rho, and it is denoted by the sign kappa. It is not K, it is kappa. Okay. So rho, from this relation you can see rho is equal to AR by L. AR by L. So 1 by rho will be L by AR. Right? Now L by A, this is cell constant, and we know that 1 by R is conductance. Right? So ultimately the relationship of specific conductance with conductance is by this equation. So kappa, that is specific resistance or conductivity, is equal to cell constant into conductance. Okay. Actually, two things you can do. Individually, you can remember all these relationships between different terms. But suppose if you are remembering, if you are able to remember one equation carefully, and if you know what are the meaning of the other terms, you can easily find out what will be the relation. Because if you know that R is equal to rho into L by A, so obviously you can establish this last relationship. So each time it is not that you have to remember all these relationship individually. Just try to remember one specific equation, and from that you can easily derive the other ones. Fine. Now we will go into details of specific conductance, because this will be from now it will be, you will see its use is very frequent. Okay. In the case of electrolytic solutions, the specific conductance, it is how it is defined. Just look at this equation carefully. Kappa will be equal to C, that is conductance, only when this L value is unity and A value is also unity. Right? So suppose L is 1 centimeter and A is 1 centimeter square. So in that case, kappa will be equal to C. Okay. So that is written here, that specific conductance is defined as the conductance of a solution of definite dilution. So there is a particular concentration, and this definite dilution, so definite diluted solution, that is present, that is enclosed in a cell having 2 electrodes of unit area. That means now A equal to 1, separated by 1 centimeter apart. That means now L value is also 1. Okay. So only when these two are 1, then only kappa can be equal to C. So you can also consider this cell. So here electrolyte is present inside the cell, and this is 1 centimeter apart, this is also 1 centimeter. That means the cube that we are seeing here, the volume will be 1 centimeter cube. So it is a volume, unit volume. So we can also say it in different way, that specific conductance is basically the conductance of a solution of definite dilution which is present in unit volume, because unit volume is same as unit area and unit length, because a volume will be ultimately area into length, right? So that is why if we say that it is unit volume, then also it is cut. Now conductance, we know its unit is ohm inverse, and L by A, that is cell constant, its unit is centimeter inverse, because this is centimeter, this is centimeter in square. So obviously it will be centimeter inverse. So the unit of specific conductance is ohm inverse and centimeter inverse. Okay. And here Next, so this is the relationship between resistivity and conductivity. These two are basically reciprocal to each other. And now we know what is specific conductance. So see, why it is specific? Because when it is normal conductance, we have not specified anything. That is why the cell, that is the electrodes are 1 centimeter apart or whatever, any other value. We have not mentioned any specific conditions. So conductance is simply the capacity to flow, capacity of flowing of electricity. But when we are saying that specific, that means now we have restricted the volume in which the electrolyte is present. So that is why the name is specific. Okay, so this is a restricted volume, and whatever ions will be present in this restricted area, the corresponding conductance we will call specific conductance. Fine. And remember, when we are decreasing the concentration, obviously the number of ions in this unit cell, that will decrease, right? And when you are increasing the concentration, the number of ions, plus minus, that is positive ions, negative ions, all these will increase. Okay, so why I am saying this? Because after some time you will see that how with dilution specific conductance is changing. Okay, this relation is very important. Now after specific conductance, there is molar conductance. Now why it is specific we have already mentioned, because now the volume is specified and the name here is molar. So obviously the solution will be of 1 mole of the electrolyte. Okay, now why we have introduced a new term, molar conductance? Why not specific conductance is enough? Why molar conductance is required? So there is some reason behind that. Suppose there is solutions of different electrolytes, so their conductivity will also be different. That is specific conductance, that will be different. Specific conductance also known as conductivity. And in the same solvent, so solvent is same but electrolytes are different. Okay, so conductivity will also be different. Obviously temperature is fixed because these are the variables. If you change the solvent, the conductivity will also change. So, and if you change temperature, conductivity will also change. So we have to fix the other variables, then only you can compare. Suppose there is any variable A, and A is dependent on X, A is dependent on Y, it is also dependent on Z. And now you want to know what is the relationship of A and X, how A is changing with X. So if you want to know that, you have to fix the other 2 variables, then only you can understand the relationship between these two. Similarly, when you want to know the relationship between A and Y, you have to fix X and Z. Okay, so that is why, as conductivity is dependent on so many things, solvent, nature of electrolyte, temperature, so now we are comparing the different electrolytes. So obviously we have to fix the solvent, we have to fix the temperature. Okay, so conductivity of solution of different electrolytes with fixed solvent and fixed temperature, it will differ because of the charge and size of the ions in which they dissociate. So as you have taken different types of electrolytes, obviously the charge of the ions, the size of the ions, everything will differ. Okay, so that is why now differs due to charge and size of the ions in which they dissociate, and also because of the concentration of ions, and or the ease with which the ions move under a potential gradient. So ease with which, it means mobility. You can say it is a mobility. That is how much mobile is the ions, because higher is the mobility, higher will be the movement, higher will be the electricity. Okay, so all these things will vary. So specific conductance or conductivity, it is not a very suitable quantity to measure conductance of different dilution. So now what we will do, we will fix the concentration. So that is why now we will take electrolyte of only 1 mole. that is the electrolyte that we are taking, it is only of 1. So the amount of from 1 mole of electrolyte, the dissociation that is the ions that we will get, the corresponding conductance, that will be called molar conductance. So as specific conductance is not a suitable quantity, so that we can measure conductance of different solution and we can compare them. So that is why it becomes necessary to define a physically more meaningful quality, which is known as molar conductance. So this is the reason why we have introduced a new term, and it is defined as the conductance of all the ions which is produced by ionization of 1 mole of an electrolyte. So in the specific conductance, what we have seen, that whatever is the number of ions, suppose in the unit volume, in one case there is 100 ions, another case there is 200 ions, but volume is fixed, number of ions are not fixed. But when we are having molar conductance, now the number of ions, they are fixed, because only from 1 mole the ions that you can get, the corresponding conductance will be molar conductance. And how it is related to specific conductance? Molar conductance, which is denoted by this sign, it is known as lambda. Sometimes you can also see it is mentioned like this. So this is equal to conductivity, that is kappa, into V. Now this V is not any normal volume, be very careful, this is actually molar volume. You can also put a suffix m, because V is the volume in ml, remember it is in ml, which is containing 1 ml of the electrolyte. So that is why it is molar volume, because it is that specific volume in which only 1 ml of the electrolyte is present. So that is why it is molar volume. So this is the relationship between molar conductance and specific conductance or conductivity. So lambda m is equal to kappa into Vm. Now here you can see another equation. This we have already seen, this is same. But how we are getting this? Remember here C is concentration in molarity. Okay, so we know that V is that volume in which 1 mole is present, right? So in place of Vm, why we have written 1000 by C? So see how we are getting this. As C is molarity, so according to the definition of molarity, it means that in 1 liter solution, C moles of the electrolyte is present, and 1 liter means 1000 ml or 1000 cc. So now we can say that C number of moles present in 1000 ml. Why we are using ml? Why we are not using 1 liter? Because it is mentioned that it is in ml. So C moles present in 1000 ml, but we require that volume where only 1 mole is present. So 1 mole is present in 1000 by CmL. So that is why in place of Vm, now we have written 1000 by C. Remember, this is possible only, it is true only when it is in ml. But suppose if in the problem or numerical, if it is not mentioned in ml, suppose the concentration is given in moles per meter cube or moles per decimeter cube, if it is not given in ml, then always use this equation. And if it is directly given in ml and kappa its unit is also in centimeter, then only you can use directly this formula. But if it is any other units are given instead of ml, suppose there is any other unit for volume, then you should use this equation, that is kappa into Vm. And by this calculation you can easily find out what will be the volume of this Vm, because if you know the concentration, so you will obviously know how to calculate this Vm, which is molar volume. Here we have units for this molar conductance. So as it is equal to kappa into 1000 by C, and kappa unit we have already seen, it is ohm inverse centimeter inverse, but ohm inverse is also known as Siemens. So that is why you can also write S centimeter inverse, and this is concentration. But now see, when we were using this equation, concentration is not moles per liter, it is more per ml or per cc. Cc means centimeter cube, cc, ml, centimeter cube, all are basically same. Okay, so mole per centimeter cube means moles per ml. Okay, because here if we want to know what is the unit of lambda m, that is molar conductance, we have to put the unit of kappa and c, and ultimately what unit we are getting here, centimeter minus 3. Now when it will be in the numerator, it will be centimeter square. So ohm inverse centimeter square per mole. Now mole will be per mole, or you can also write in place of ohm inverse S. Okay, sometime in problem if you see the mention of ms, that means it is millisiemens. Okay, ms means millisiemens. So this is molar conductance. Now there is a third type of conductance which is known as equivalent conductance. So now from the name itself you can understand, as in case of molar conductance, what we have mentioned, it is the conductance of all the ions by the ionization of 1 mole. But when we are saying equivalent conductance, it will be by all the ions which is produced from one equivalent of the electrolyte. So total 3 types of conductance: specific conductance, which is kappa, another name is conductivity, second one is molar conductance, sometimes it is also called as molar conductivity, and the third one is equivalent conductance or equivalent conductivity. So what is equivalent conductance? It is defined as the conductance of all the ions produced by one equivalent of an electrolyte in a given solution. Sometimes you will see in some books it is mentioned 1 gram equivalent. Actually both are same, 1 equivalent or 1 gram equivalent. Also in molar conductance you can see it is mentioned 1 mole of the electrolyte or 1 gram mole of the electrolyte. That is, both are same. So this is the equivalent conductance. And here also we have same type of relationship, that is now instead of lambda m we are writing lambda equivalent. Kappa is still there. Now V. Now this V is not molar volume. This volume is that particular volume in which only one equivalent of the electrolyte is present. Okay, and in the previous case, the relationship, in the relationship what you have seen here, C is written, and C is mainly the concentration in terms of moles, but now it is in terms of equivalent, that is why N is written. Okay, so suppose the concentration of the solution is given in terms of normality. Okay, suppose it is X normal solution. Okay, so what you will say? You will say that X normal solution is presenting 1000 ml. Sorry, X equivalent of the electrolyte is present in 1000 ml according to the definition of normality. Normality definition means the number of equivalent of the compound present in 1 liter or 1000 ml. So when it is X normal solution, what will say? That X equivalent of the electrolyte is present in 1000 ml. But we require only that volume which is containing only one equivalent. So if X equivalent is present in 1000 ml, so one equivalent will be present in 1000 by X, right? And here this X actually if you consider it as normality, so that is why it is N is written. But just try to understand the concept. Don't blindly just remember all these formulas. How you are getting the formulas, that is the important thing. So this relationship will be true when this N, that is the concentration, is mentioned in normality, then directly you can use this equation. But suppose if the concentration is not given in terms of normality, suppose it is given equivalent per meter cube or per decimeter cube, in that case you should use this formula. because V is nothing but this one. This is actually the V. Okay, and here if you, that is, you can also write the equation in this way so that you can find the difference between this previous equation, because in the previous equation also we have written V, but you can use Vm for the previous equation, and in this case you can use Ve. Ve means the volume in which equivalent amount is present, so that you can easily understand what is the difference between these two. So when it is lambda m, it is kappa 1000 by molarity, but when it is equivalent, it is kappa 1000 by normality. Okay, and if concentration is not given in terms of molarity or normality, always use this equation. Fine. So unit same as we have seen in the previous case. Kappa is S centimeter inverse or ohm inverse centimeter inverse, and N is in equivalent per centimeter cube, that is equivalent per ml. In the previous case, that is molar conductance, we have mentioned moles per centimeter cube, but now it will be equivalent per centimeter cube. So ultimately the unit will be S centimeter square per equivalent. This is the unit of lambda equivalent, that is equivalent conductance. Now from these two equations you can find out that two equation, I mean to say this equation. Suppose this is number 1 equation, this is number 2 equation. So what we are trying to do? We are trying to do what is the relationship between equivalent conductance and molar conductance. Okay, but before that we have to know what is the relationship between normality and molarity. So suppose for the same compound, the concentration it is mentioned in normality, another concentration is mentioned, that is the same concentration is mentioned in molarity. So what is the relationship between these two? N is equal to N into M. Okay, so what it means? N into M means N is N factor. And N factor means, suppose if it is acid or base, then directly you can consider the acidity or basicity. So suppose if it is HCl, its basicity is simply 1 because you are getting only one replaceable hydrogen. But if it is H2SO4, its basicity will be 2 because there are 2 replaceable hydrogen. So now the N factor will be 2. And if it is any molecule like that, AlCl3, so here the total charge, positive charge is plus 3 and total negative charge is also minus 3, because for each chloride it is minus 1, so 3 into minus 1 minus 3. So for AlCl3, this type of salt, N value will be 3. Okay, so this is a relationship between normality and molarity. And N, sometimes it is also mentioned as small z, which because we know that charge is mainly expressed by z. So in case of this salt, in case of acid base it is acidity basicity, fine, but when it is salt it is the total positive charge or total negative charge, because positive and negative charge both will be, magnitude will always be same, because ultimately the molecule is neutral. So Z, as it is charged, so that is why small n can also be mentioned as small z. So now what we will do? Equation 1 divided by equation 2. So it will be lambda m, lambda e, and 1000 kappa by m, kappa into 1000. So these two will be cancelled. So ultimately what we are getting? N by m. Now what is n? In place of n, now we will write small n into capital M. So these two will be cancelled. So ultimately the relationship, so it is lambda m by lambda equivalent. This is actually equal to small n or z. Okay. So suppose if this one is given, if you know the n factor, you can easily find out what will be the unknown conductance. And if lambda e is given, then also you can find out lambda m. Okay. So this relationship is also very important. So three types of conductance we have seen: specific, molar, equivalent. In case of specific, it is 1 unit volume. In case of molar, it is 1 mole of electrolyte. And in case of equivalent conductance, it is 1 equivalent of the electrolyte. Now, what are the factors that affects conductance? Okay, so we are now using conductance, which is the general term. That is it. Though we know there are three types, that is specific, molar, and equivalent conductance. Okay, but here we are trying to see what are the factors that affects conductance in general. So temperature. Conductance of an electrolyte solution increases with increase in temperature. Now this is true only for lambda m and E, because for specific conductance it is different relation with temperature, and mostly we are here focusing on these two, not specific conductance, that is kappa, not this one. Because why it is not, we are not considering here, because in case of kappa there is a fixed volume, that is unit volume, and whatever is the number of ions present in that fixed volume, that conductance will be specific conductance. So when you are increasing the temperature, dissociation will increase, so number of ions will also increase. So what will happen? Your volume is fixed, which is 1 unit volume. So as number of ions are, that is increasing in that particular volume, okay, so there will be, that is the conductance of an electrolyte solution increases with increase in the temperature due to increase in the extent of ionization. So in case of lambda m and lambda e, we have not any fixed volume, right? But in case of kappa, we have fixed volume. So when temperature we are increasing, there will be increase in the value of ions, number of ions. Sorry, it will also increase. That is, I have wrongly mentioned this. All this will increase actually with increase in temperature. And here the next variable is, so for these two directly proportional to temperature, but kappa, it is related to temperature in a different way. Okay, it is actually decreasing with increase in temperature. Now why it is so? Because as the volume is fixed and number of ions are increasing, but as the volume is fixed, though number of ions are high, but as the space is fixed, so mobility will not be as before. So as a result, though number of ions are increased, but because of this decrease in mobility, the conductance, that will also decrease. So this temperature dependence that is mentioned here, that is the conductance of an electrolyte solution increases with increase in temperature, it is only for these two, that is molar and equivalent conductance, not for kappa. You will see that kappa always it varies with some variables which is not matching with lambda m or lambda et. It is completely different. Okay, because in case of these two we have not fixed the volume, but in case of kappa the volume is fixed, and in case of these two, as number of ions are increasing and volume is not fixed, so there is no problem with mobility. Okay, the second point is ionic size and mobility. The ionic mobility decreases with increase in its size, and hence conductivity also decreases. So suppose we have two ions, cesium ion and lithium plus ion. Now obviously lithium is shorter in size, cesium is having larger size. So which one will have higher mobility? Lithium plus will have higher mobility, because smaller is the size, higher is the mobility. So it decreases with increases, opposite relationship. Okay, now remember this is in molten state, that means there is no sign of water. But suppose if it is aqueous solution, now the case is completely different. So when it is aqueous solution, what will happen? As lithium plus, it is very small, and its solvation power is very high, it will be highly solvated by water molecules. So all these are water molecules. So when it is hydrated ions, now see, though lithium is smaller in size when it is free ion compared to cesium plus, but as in the hydrated condition it is highly solvated, so it now becomes larger. So now the size is higher for lithium because it is hydrated. So now as it is larger, it will move slowly, and this is smaller, this will move slowly, this will move fast. So basically, if you want to know the mobility, you have to know whether it is aqueous solution or molten state, because molten state means no solvation, and no solvation means no hydrated ions. It is simply the naked ion, free ion. Fine. Number 3, concentration. Now see, it is specifically mentioned that specific conductance, that is kappa, it increases with increase in concentration of the solution, okay, as the number of ions per unit volume increases, whereas both the equivalent conductivity and molar conductance increase with decrease in concentration. Now why it is so? Now decrease in concentration means now it is more diluted. Now as I have already mentioned, that dissociation increases when the solution is more dilute, because in dilute condition the extent of ionization increases. So extent of ionization increases. This is specifically important for weak electrolyte, because we know that if it is strong electrolyte, dissociation is, whatever is the dilution, dissociation is mostly near 100%. That is why it is strong electrolyte. It will always remain in dissociated state. But if it is weak electrolyte, the effect of dilution is very high compared to strong electrolyte, because with decrease in concentration, that is the more dilute is the solution, higher will be the ionization. Okay, so when we are decreasing the concentration, these two are increasing. That means with dilution it is directly proportional, but with concentration it is inversely proportional, because concentration and dilution, these two are inversely proportional. Okay, next factor is nature of electrolyte. The strong electrolytes, that is nature of electrolyte means two types of electrolytes, strong or weak. They will undergo complete ionization. Obviously they will show higher conductivities since they furnish more number of ions, and for electrolyte, higher is the number of ions, higher will be the electricity. But for weak electrolytes, as there is partial ionization, suppose 50% or 80%, hence it will show comparatively low conductivities in their solution, provided all other variables are fixed. Under that condition, nature of electrolyte, if we compare, obviously from strong electrolyte, as the number of ions are very high, so electricity that we will get from it, that will also be very high. So these are the 4 factors on which conductance is dependent. So now we will compare all these 3 types of conductance, and here we also have the unit. So when it is in general, we say conductance, it is the property of the conductor which facilitates the flow of electrons. So this is a property or capacity of the flow of electrons. Higher is the capacity, higher will be the conductance. But these conductance, there are 3 types. So when the conductance of a solution of definite dilution enclosed in a cell having 2 electrodes of unit area separated by 1 centimeter apart, which is nothing but 1 unit volume, it is denoted as kappa. Unit is ohm inverse centimeter inverse. Okay, and ohm inverse, it is also called as centimeter inverse, or it is mho. All are same. Then we have equivalent conductance. So when we are using the term equivalent, so it means that it will be the conductance of all the ions which is produced by 1 gram equivalent or simply 1 equivalent of an electrolyte in a given solution. So and now the unit will be, so how we have derived this unit, that we have also seen. Ohm inverse centimeter square per equivalent, or it may be written as Siemens, that is S, or it may be written as mho. And when it is molar conductance, same definition like equivalent conductance, but now the difference is only here. It is 1 mole of an electrolyte in a given solution. But sometimes this it is denoted by lambda equivalent, or this one lambda m, this is also called lambda. Okay, now these two, how they are related, that we have seen. N, where n is n factor, or the total positive charge or total negative charge. But suppose if it is 1, for example for NaCl, because total charge is +1, total negative charge -1, or KCl or KOH, K plus HO minus, all are single positive charge, single negative charge. So in that case, basically these two will be same. So these two will be different only for some special cases where equivalent amount and mole amount, these two are not same. So for example AlCl3 or H2SO4 or barium chloride, all these are examples. So here charge is 2 plus, total negative charge is 2 minus. AlCl3 we have seen already, then it is also true for H2SO4. So in this case these two will not be same. Okay, so obviously here in case of AlCl3, suppose this value is 3, that means lambda m, that will be greater than lambda e. Okay, so molar conductance will be higher than equivalent conductance. But if it is n value is 1, that is for NaCl or KCl or KOH, NaOH, then these two will be same value. Equivalent conductance, molar conductance, both are same. And look at the unit. These two units are actually same, only here we have equivalent, but in this case it is mole inverse. That is the only difference. Okay, sometimes you can also see that in place of centimeter it is mentioned meter square. That may be also the case. So be very careful about the units whenever you are solving any numerical, because if it is given, if sometimes it is specifically mentioned that express the answer in meter cube, but if you are expressing it in centimeter square, obviously the value will change. Okay, so that is be very careful about the units and how to change the unit from one to another, that is from centimeter to meter or meter to centimeter. These are very frequent whenever we will try to solve any numerical.